Hi folks, welcome back to Physics with Captain Rod. Purpose of this video is to just go through an example of how to handle a DC voltage source hooked to a circuit that has both capacitors and resistors. So what we're looking at, we have this 24 volt DC voltage source. It's hooked to a 10 microfarad capacitor, a 3 microfarad capacitor. We've got a 4 ohm resistor in here and an 8 ohm resistor with this switch connecting these parts of the circuit. What we're going to do here is we're going to try to find the charge on each capacitor with the switch open and closed for a long time. So I think I'm going to start with the switch open. If the switch is open and I look at the color and I color code the potentials, this is what we have going on. This should all be constant potential up to this point. Over here, this would be constant potential, and here's an important thing to realize. With the switch open and this circuit having been constructed for a long time, this capacitor would be fully charged. At that point, there would be no current in this branch, which means the voltage across this resistor would be zero. So this red will go all the way down to here. We'd have a voltage drop across the capacitor. And we're back to the black voltage here, and again there'd be no voltage across this resistor. So very important to realize that there's only two voltages in this problem if the switch has been open for quite some time. So I'm going to go ahead and get rid of that red, because when I close the switch I'm going to want to redo the color codes. So it's important to note that there's only one voltage in this problem, 24 volts here, 24 here, 24 here. So this capacitor is going to be charged to this polarity, plus minus. The charge on it I'm going to call Q1. Over here we've got a Q2. Q1 is going to equal the voltage across that capacitor, 24 volts times 10 microfarads, and we get 240 microcoulombs. So that's the charge on that capacitor with the switch open. Again, I'll put the qualifier for a long time. All right. Now, again, this 24 volts, we'd have no voltage across here, so the voltage across this capacitor also 24 volts. So Q2 is going to equal the voltage, 24 volts, times 30 microfarads, and I get 720 microcoulombs out of that. And again, don't forget that farad is a coulomb per volt. So we're taking volts times coulombs per volt. We end up with coulombs out of it, and I'm just treating the micro like a unit, so microcoulombs. So that's what the problem looks like with the switch open for a long time. All right, on the right here we're going to talk about what it looks like if the switch is closed for a long time. And again, the reason I'm attaching the word for a long time is because when this switch closes, these capacitors are going to have a tendency, or they're going to have the ability to discharge some. So what's going to happen is we're going to have some time-dependent currents there for a little while. And for just a short time frame, we're going to have three currents. We're going to have a current in this branch. Then we're going to have a current in this branch, current in this branch, and we'll have currents across here, here, and here. So it's a reasonably complex problem here while the switch is closed. However, if it's closed for a long time, here's what we can say. Eventually, this capacitor is going to hit its steady value, and so is this one. When that occurs, there will be no current in this part of the circuit or in this part of the circuit. And that means there's really only one path for current to take. There's only going to be one current, and that current will be in this branch, down through this resistor, through here, and back. So we're only going to have one current in this problem when the switch has been closed for a long time. So I'm going to go ahead and start right here, write a Kirchhoff's equation here. So again, I imagine my little ladybug here, and that ladybug jumps across this resistor. Ladybug goes up 24 volts in potential. Ladybug takes this path, jumps across this resistor here. I think I said resistor before, I meant battery. Ladybug jumps over the battery, goes up 24 volts in potential. Ladybug gets across here, jumps across the resistor. That ladybug is now going to drop in potential by an amount IR. Right. Ladybug's just following the path where there's current. At this point, Ladybug jumps across this resistor, drops in potential by an amount I times R, and that R would be 8 ohms. Now that ladybug's back to where she started, so that sum equals 0. So here's an equation we can solve for I, for the current in the loop. We got 24 volts equals, by the time I add this to the right, we're going to get I times 12 ohms. I'll go ahead and put that in parentheses. It's not too hard to show that that current is 2 amps. All right, so we have a 2 amp current. Now, the current doesn't directly tell us what the charges are on the capacitor. However, if I color code the potentials again, and again, this is all constant potential because that's all conducting material up to that point into there. Now, at this point, there is a voltage drop across that resistor. So now, actually, let me go to my color wheel here, and I'll color code that potential orange to here. Then there's going to be a voltage drop across the resistor and across the capacitor. Now this would all be one voltage. I'm just going to leave that black. So now that the switch is closed, now we have 3 different potentials here. We've got the red potential, orange potential, black potential. An important thing to recognize is that the potential across this resistor is red to orange, and it's the same as across this battery. So that potential can be calculated easily, by Ohm's law. V equals I, which we know to be 2 amps, times R, 4 ohms, and we get an 8 volt potential. Before I move on, I'm now just going to calculate the charge on that capacitor, because that capacitor has the same voltage across it, red to orange. In our red to orange voltage, we just calculated it at 8 volts. So we're going to have 8 volts times the capacitance of 10 microfarads, and we get 80 microcoulombs out of that. All right, well now I'm going to go ahead and calculate the voltage across that resistor, which again is going to be IR, which is going to be, where'd it go, 2 amps times 8 ohms, or in other words, 16 volts. And in case you're wondering, I did choose numbers so that these would, I choose resistor values so that the currents and the voltages would come out all nice, but that's okay. You conceptually work the problem the same way regardless of what resistor values are here. The voltage that I calculated is orange to black, and I take a look over here and I notice it's orange to black across that capacitor, so I can now calculate the charge on that capacitor by taking the voltage across it, 16 volts, and multiplying by its capacitance, 30 microfarads. So let's see if we multiply that out. Let's see, 16 times 3, I believe is 48, so that's 480 microcoulombs on charge 2. So again, switch open for a long time, 240 and 720, and it's important to note that if the switch is open, everyone needs to conclude that there must be 24 volts across each capacitor, because if the switch has been open for a long time, there's going to be no current in these branches, meaning that there'd be no current through these resistors either, and therefore no voltage across them. However, with the switch closed, now we have currents through these resistors, or I should say a current through both resistors. It's the same current. A very important thing to realize in this problem is that 2 amps is good anywhere along this path. You put an amp meter anywhere in there, it's going to read 2 amps. That current allows us to calculate the voltages across the resistors. Very important thing to recognize is that the voltage across the resistor is the same as the voltage across this capacitor. You can also see that from Kirchhoff's law, because if we do a loop, if I called, we called the voltage here C or V, it'd be plus V and then minus IR equals 0 if we write a loop for this. Or we can see it from the color code, red to orange, red to orange. Same thing down here, the voltage across this resistor, orange to black, voltage across here, orange to black. Therefore, it's the same. So we can calculate the voltage here, use that same voltage on this capacitor to find the charges. Hope this video helps demonstrate how to look at RC types of circuits, at least for a long time. It takes quite a bit more math to look at these in the time-dependent range, and I'll make some videos that are about the time dependency of RC circuits. But anyway, hopefully this helped. Have a great day.